Imagine trying to catch a waterfall in a thimble. That's exactly what it feels like managing performance data from modern telecom networks. Welcome to this explainer. Today we're talking about performance management data, the kind that's collected continuously from thousands upon thousands of network elements. We're talking antennas, base stations, radio units, and every single one of them is reporting hundreds of distinct performance counters every few minutes. The engineering challenge here is absolutely massive. It isn't just about finding enough hard drives to store all this data. The real test is making it fast and cheap to actually query that data for key performance indicators, or KPIs, at an analytical scale. So we're going to dig into a really fascinating architectural case study of how a massive telecom platform was completely redesigned from the ground up to query billions of records efficiently.
14 million. Yeah, you heard that right. That's 14 million records. And we're not talking per month or even per day, that's per hour. That is the hourly insert rate of data just flowing into the system from vendor telecom antennas. If your database architecture isn't totally dialed in, an insert rate like this is going to make your entire platform basically buckle under its own weight.
Okay, so let's dive right into this architectural blueprint. We are going to tear down a broken system and rebuild it step by step. We'll start by diagnosing the 14 million record bottleneck and then look at escaping the JSON trap. From there, we implement the real solutions, flattening the data columns, taming the ingestion pipeline, and serving fast with Go. Finally, we'll see the payoff in billions of records, milliseconds. Let's get to it.
All right, Section 1, the 14 million record bottleneck. Let's diagnose exactly where things were failing.
To really understand the bottleneck, we have to look at the old architecture. It centered heavily around a component called the PM parser. Now, its whole job was to read raw performance management files delivered by the network vendors and then load them into ClickHouse. But notice that final measurements column. Instead of organizing the data properly, the system just dumped hundreds of distinct measurement counters into one single massive JSON-string column per cell per timestamp. Sure, at ingestion time, this probably felt super convenient. The parser just serialized the whole payload as a string, wrote one row, and called it a day. But downstream, this created an absolute nightmare.
Which brings us to Section 2, escaping the JSON trap. Here's why that convenient JSON totally failed us.
So, that highly convenient JSON-string payload, it actually set off a catastrophic domino effect for the engineering team. First off, it forced the back-end application to do really slow, miserable math on the fly. Just imagine a user wants to know the radio resource control success rate. To calculate that one metric, the back-end had to fetch millions of rows, deserialize the JSON string right there in the application code, pull out the success and attempt counters, and then run the arithmetic. With 14 million records pouring in every hour, doing this live was totally unsustainable. Second, ClickHouse is a columnar database, but those columnar strengths were being completely wasted. And third, the team initially tried to patch this by using ClickHouse materialized views to flatten the JSON on insert, but at that 14 million an hour rate, materialized views introduced fatal write amplification. They lagged, and query performance basically went off a cliff.
The original architects actually hit the nail on the head when diagnosing this. They said, JSON columns are convenient for flexible schemas, but they trade away the columnar performance that makes ClickHouse fast. ClickHouse is literally purpose-built to compress data efficiently and read only the specific columns you request. But because everything was just packed into a single string, the database was forced to scan and deserialize the entire massive JSON blob for every single row, even if you just needed 2 counters out of 200. If you're forcing your database to scan the whole haystack just to find a single needle, your platform is for sure going to break eventually.
Moving on to Section 3, flattening the data columns. It's time for a new storage schema.
So here is the first major fix, a complete ground-up revamp of the storage schema. In the old architecture, you had one row with a single JSON blob holding all the counters, right? Well, the core insight for the new architecture is beautifully simple. Store each measurement counter as its own independent column. The new target table uses a merge tree partitioned by day. Now, each row contains the base cell dimensions plus a dedicated nullable float 64 column for every single counter. This means if a KPI query needs just 2 counters, it asks ClickHouse to read just those 2 narrow columns out of the hundreds available. This simple change drops I/O and CPU costs by roughly 2 orders of magnitude compared to scanning that old JSON string.
Now, you might be wondering, wait, telecom vendors ship new performance counters in software updates all the time without any warning. If we use flat columns, won't the pipeline just break the second a new counter appears? And that is a great question. The answer is automated schema evolution. They built this brilliant airflow step that scans recent raw data, discovers any new counter keys hanging out in the JSON that don't have a column yet, and automatically issues an alter table add column if not exists command. It's a self-healing trick that handles new counters instantly, zero manual intervention required, completely preventing data loss.
Okay, but wait, if you have hundreds of flat columns, doesn't that completely bloat your physical storage layer? Actually, no, because a lot of counters are just null for a given cell during a given time interval. ClickHouse uses native features like sparse serialization and ZSTD Level 1 compression. These techniques compress all that empty space so incredibly well that the storage overhead remains completely manageable, even as you scale up to hundreds of these flat columns.
Okay, Section 4, Taming the Ingestion Pipeline. Kafka to the rescue.
To transition from those synchronous failures to real asynchronous stability, the architects brought in Kafka. Think of Kafka like a massive sponge placed right between the PM parser and ClickHouse. It explicitly controls the ingestion rate, absorbing those massive data bursts without letting the database choke under the 14 million hourly inserts. ClickHouse just reads from these topics using its native Kafka table engine. This gracefully decouples how fast data is produced from how fast it's committed. It gives the system an essential buffer, crucial backpressure, and the ability to replay data if a downstream write fails. So instead of triggering synchronous materialized views on every single write, inserts now flow smoothly through a highly controlled, stable pipeline.
And to replace that crushing on-the-fly math we talked about earlier, all the computation was pushed to a scheduled pipeline using Airflow DAGs. Here's how these background workers get it done. First, DDL initialization runs to make sure the target table is ready and waiting. Second, Schema Sync steps in to auto-discover those new columns we mentioned. Finally, the real heavy lifter takes over, sliding window ingestion. Running every hour, this process fetches raw rows in 10-minute chunks, deserializes the JSON in Python, inserts the flattened rows, and pre-calculates all the KPIs asynchronously in the background, meaning the heavy lifting is completely finished before the user ever even clicks a button.
Section 5, Serving Fast with Go. Time to upgrade the backend.
So this brings us to the final piece of the puzzle, the user-facing back-end application. The old system was relying on a super CPU-heavy Django application. Literally every API call triggered a massive database query, JSON deserialization, and complex arithmetic on millions of rows. Django was just sweating under the immense server load, and it was agonizingly slow. The new system rips all of that out and replaces it with a lightweight Go backend. Go's low memory footprint and high concurrency are just perfect for read-heavy API workloads. And here's the best part. Because Airflow already pre-calculated the KPIs, this Go backend doesn't do any complex math. It simply queries a compact result table and hands the data back to the user instantly.
Section 6, Billions of Records, Milliseconds. Let's look at the compounding gains. When we step back and look at these architectural upgrades side by side, the compounding gains are just incredible. Measurement storage evolved from a bloated JSON string to precise flat columns. Because of that, ClickHouse scans went from having to read the full JSON blob for every row to exclusively reading just the queried columns. We pushed KPI calculation from expensive, on-the-fly requests to background pre-calculations via Airflow. We fixed insert handling by ditching those slow materialized views for a buffered Kafka engine. And finally, we upgraded the backend from CPU-heavy Django to lightweight, lightning-fast Go. The final result really says it all. Query response times went from sluggish seconds, or even minutes in some cases, down to milliseconds, a true game changer. Let's anchor back to that immense scale we discussed at the very start of this explainer. 10 billion records. With this new flat columnar stack in place, the platform easily sustains over 336 million records per day. That is approaching 10 billion records every single month. And even at that staggering volume, this architecture provides highly stable ingestion, fast automated schema evolution, and sub-second KPI query latency without breaking a sweat. So I'm going to leave you with this provocative question to chew on regarding your own data pipelines. How much performance is your system currently sacrificing by prioritizing flexible JSON over native columnar speed? You know, it's incredibly easy to default to nested JSON because it feels so convenient up front. But as we've clearly seen today, flat beats nested at analytical scale every single time. Thank you so much for joining me for this explainer, and I really hope this deep dive empowers you to rethink and optimize the bottlenecks in your own platforms.